All right, I'm just going to do a couple of examples of how to figure out intermolecular forces for a particular molecule. So the two examples in your notes, the first one is H2O2, okay? And then the first thing you always need to do is figure out what it looks like in 3 dimensions. So the first step is going to be to draw the Lewis structure. So this is a little bit of a review. So if you have 2 hydrogens, each hydrogen has 1 valence electron, and we have 2 of them. Right? And each oxygen has 6 valence electrons, and we have 2 of them. So that will give us a total of 14 electrons for this molecule. Okay, so hydrogen can never go in the middle, so we're going to have to draw it like that, okay, because hydrogen has to go on the ends. Okay, and now we've used up 2, 4, 6 electrons in our bonds, which means we have 8 more. Hydrogens are both done. 2 is all they get, remember? So each of these oxygens has 4, and we'll give them each 4 more to get to a full octet. Okay, so now what does this look like in 3 dimensions? I've drawn it in a line, but this isn't actually a linear molecule. Okay, because there are lone pairs on each of these oxygens, those are electron groups that take up space. Okay, and so what you'll end up with, if we look at the geometry of just one oxygen, each one has 4 electron groups, so each of these will be tetrahedral. Okay, so if I were to try to draw that in 3 dimensions, I'll have my oxygens bonded to each other. All right, that's going to be my one bond that's the same. And then I'll have a hydrogen coming out on one, and then my 2 lone pairs here. And then a hydrogen going back or coming out on the other. Okay, so this is not a linear molecule. It kind of zigzags. Okay, so what that tells us is that the electrons, and I'll draw our electron groups on here to kind of give us a sense of what's going on. So the electrons are not going to be shared equally on both sides. Okay, so this oxygen is more electronegative than the hydrogen, so it's going to pull electrons this way. All right, so we'll get a partial minus up here and a partial plus down here. All right, and then the opposite will happen here. The electrons will go this way, and we'll get a partial minus and a partial plus. Okay, so we have negative charge here and here on our molecule and positive charge there and there. Okay, so there are 3 different kinds of intermolecular forces we learned about that would apply to molecules. The first one is dispersion. All right, everything has dispersion. So the answer to does it have dispersion forces is always yes. Okay, polar molecules, nonpolar molecules, they all have dispersion forces. All right, we just determined that this molecule is polar. So for dipole, it will also be able to do that because it's a polar molecule. All right, and then the last type is hydrogen bonding. Okay, and we can get hydrogen bonding because we have a hydrogen, we have to have that first, and that hydrogen needs to be bonded to an oxygen, a nitrogen, or a fluorine. So if we have an HF bond, an HN bond, or an HO bond, yes to any of those means yes to hydrogen bonding, and we have this one. So in our case, this molecule can do all 3. It can hydrogen bond, it can make dipole-dipole interactions, and it can have dispersion forces. All right, so now let's go ahead and look at the second example, which is NH3. Okay, so NH3, the first thing we're going to do is draw draw the Lewis structure. So we need to figure out how many valence electrons it has. So nitrogen has 5. Each hydrogen has 1, but there are 3 of them. So in total, we have 8 electrons to work with in this molecule. Okay, nitrogen will go in the middle, and all of the hydrogens around it, because remember, hydrogen can't go in the middle. That is 2, 4, 6 electrons. So we have 2 left, and they will go on the nitrogen to give it a full octet. All right, this nitrogen has hydrogens that are all the same, but that lone pair, remember that big negative charge that's sticking up there, is going to cause this to not be symmetrical, so it will be a polar molecule. All right, so if we wanted to draw what that looks like in 3 dimensions, all right, this will look like a tetrahedral molecule, all right, but that lone pair up here, which we don't have to draw, but we could, will be sticking up from the top. Okay, so this molecule is polar, all right, and it contains an NH bond. All right, so for intermolecular forces, this one can have dispersion because everything can. It can do dipole-dipole because it is polar, right? And it can do hydrogen bonding because it has an NH bond. Okay, so in both of these examples, it could do all of them, but I did that partly because I wanted to go through all the questions. So if this was nonpolar, then we wouldn't be able to get dipole-dipole. All right, if it didn't have any hydrogens, or if the hydrogens it had were bonded to a carbon, for example, it wouldn't be able to do hydrogen bonding. Right, so those are the 3 questions you need to keep in mind when you're determining what intermolecular forces we can do.